I think that the discussion is naturally turned into the panel discussion. So I'm gonna just share the screen with all of our speakers again, and I'll be waiting for more questions to come. But I do have a question that I think is like, how the controversial topic that was posed by Keith Lambert, and he actually posted a link to the famous paper whether a neuroscientist can understand a brain processor. So in this series of talks, we're seeing really the entire gamut from computational models to brain dynamics. And I was wondering what our three panelists right now think about that, and whether there is actually a way in which we are going to be able to go from these increasingly sophisticated methods to really making the jump from structure to function and understand really what kind of computations are performed.
Well, I'll jump right in. I typed it in the chat. I find that comparison somewhat misguided, to be honest. It's like asking, can an ornithologist understand a jet plane? Not really. I mean, jet planes have landing gears and hydraulic fluid and what have you. An ornithologist would be totally puzzled by all that. To me, brains are evolved. You know, they have these constraints on them that they have to satisfy. I think some of the things I mentioned, and cognitive architectures are a much larger space to explore, really. So I wouldn't advocate to, you know, understanding the brain in every detail is the only way that we can understand cognition. Actually, it's one way to understand a biologically realized, you know, example of cognition, but it's not the only one that's out there and that's possible to study. So I don't know. I mean, that paper, when it came out, it kind of rubbed me the wrong way, because it's really not. I don't think it's quite the right question to ask, and yet, of course, caught a lot of attention, and perhaps for the wrong reason. That's my take on it.
Yeah, and I think, you know, the other point to make here is that there's just many sources of constraint, right? We know a lot about neurons. We know a lot about, you know, the very low level, the very high level. So it's not just this one methodology that they're considering here. So if you put all those pieces together, and especially also, I'll make a plug for computational models, you know, showing how we can take those low-level neural details and show how they produce the higher level cognitive function, that, you know, you've got a pretty complete picture there. So if you just take one window on anything, it's always going to have ambiguity, and you're not going to be able to figure out how it works. But we do know a lot more than what's reflected in that paper.
Lucina?
Yeah, I don't think I have anything to add. that was a very good answer.
So a question that was asked actually some time ago by Paul Rosenblum, and it was about really a distinction between rich club and hubs. And hubs are really important in designing cognitive architectures. And you might have seen like a couple of shout outs to the common model, which is this consensus architecture that has gained interaction. But common model, of course, has a central hub. But Olaf pointed out that, you know, hubs per se are not really what gives the brain power. Is the rich club architecture. So can you please tell me more about that?
Well, to me, these hubs and rich clubs are not mutually exclusive. It's possible theoretically to have an architecture with hubs and no rich club. It turns out it looks like brains have both. Kind of makes sense when you think about it. You want those hubs to talk to each other very quickly, very directly, not have to go through multiple intermediate steps, have their signals be contaminated by noise and whatnot and conduction delays, but really sort of bring the information together in one common space, right? So from that perspective, it seems to make a lot of sense to have that in a biological nervous system. The fact that there's multiple hubs involved provides some additional variability. You know, you don't have to always engage the whole set of them. You might engage subsets of them in different contexts. Again, flexibility is the word, right? And so you know, it all made a lot of sense to me. We found it on the first try. We were kind of pleased with that. And it seems to be something that a lot of organisms have found ways to realize in their architecture. Is that the only way to do cognition? Probably not, but it might be a nice, feature of our own architecture that allows us to do things that otherwise wouldn't be possible. That's my take.
Randy and Lucina?
One follow-up question. In the cognitive architectures, the basal ganglia is like, one of the major hubs. It doesn't feature, as far as I could tell, in what you guys are talking about. So what do you think about the basal ganglia as a hub, and why is it not there, and what's going on?
I think it might not be there as an oversight more than anything else, because we're often so corticocentric in a lot of this network modeling. I don't know if that's just for historical reasons, or because it's just easier, or because we think, the time series are more comparable across cortical areas, so we feel better about comparing them. But when you do start putting in subcortical nodes like the thalamus and the basal ganglia and stuff, you do see, obviously, as you described, like they're very much involved in all these systems. So I think if they're not involved in some of the things we've shown, it's our fault for not including them. But not that they shouldn't be, just that they. I think personally, like a lot of times when we're doing these like effective connectivity modeling or something like involving DCM or Granger causality, you're limited in the number of nodes you can include. So you may say, well, I'm just going to include these 6 cortical nodes, and even though I know the basal ganglia is there, I'm going to ignore it to our own peril, I would say.
Yeah, I would agree. It's largely oversight, neglect to some extent, also methodological difficulties with thalamus particularly. It's very hard to segment the different subdivisions in human imaging. They're teeny tiny, and most imaging is just isn't really up for it. But in the rat work that I've done with Larry, and Larry is really an anatomist, through and through. It turns out there are hub regions in those, there are hub nodes in basal ganglia and subcortical subdivisions as well. And then interestingly, as you put the rat brain together, as you start zooming out, have more and more subdivisions as part of your overall architecture. These hubs change status. Some cortical hubs now suddenly are diminished in their importance, while other regions and other parts of the brain gain importance, just topologically speaking. And that tells me that there's a lot more going on than we've seen so far in human imaging.
So I have a burning question, if I might jump in, which is actually to John Laird, as he's kind of available here, as a representative of people working on these cognitive architectures. What do you think about this very kind of dynamic picture coming out of these network type of approaches, and the kind of thing I was articulating in terms of these, very distributed brain areas working together in comparison to the standard cognitive architecture picture? How do you reconcile those different views of things?
So I have to understand your ideas better, especially if it's at the fine grain of bindings of relations to things. But if you look at both, a lot of cognitive architectures, they're not that sequential. They are, a lot of things are happening in parallel all the time. So let's just take SOAR, for example, or ACT-R, is that there is this match process that we implement symbolically of comparing procedural memory to working memory. But that is, we would expect a very parallel process that's going on and distributed in many, in different areas of the brain as appropriate, or maybe, it's going to be localized in some more than others. You look at Andrea's work where he's mapped the common model cognition onto the different brain regions, and you find parallelism within those regions, but you do see, significant different activations based on what we assume is the connectivity between things like working memory, long-term declarative memory, and procedural memory, and perception and action. So all those different components are having parallel processing going on. It's not just a it's not a sequential computer with a programming counter that just going chunk chunk chunk. So I actually am going to kick it over to Andrea because he's better at answering your question probably than I am.
That's a big honor. It's hard to say, right? Because the architectures and the brain are like two complementary views, and you live in different constraints. In simplifying architecture, but at the same time having a much richer way of adding details to your models and the way they interleave. It's largely a matter of finding a way to connect the two, which actually was going to be one of the next questions, because you can think of the architecture different ways. Like at the one end, you have like models like Olaf's model, which are really structural in many ways. And then you can go down the gradient and find Lucina's work, where structure starts to predict behavior, and the structure adds a little bit of temporal richness. And then you can go to Randy's work, where actually you try to create very detailed simulations of what's going on and see if it matches the higher level things. Our work has been like in the middle ground, trying to see whether you can get like these functional constraints and see whether the functional constraints make predictions about the temporal sequence of events in the brain that actually can be traced. What we found was actually surprisingly good, because we found the same constraints are done across tasks, across individuals, which is what you imagine would be true if there was such a thing as an architecture. I would like to ask more questions about the architecture, but I would like to take a tiny detour, since we have still like a good 10 minutes, for something that actually has not come up in this session at all, but was very prominent in yesterday's sessions. And it was the social aspect. And Mark Orr had asked whether brain dynamics respond to social interactions, being in a team, interacting with other individuals as well, and whether this alters the network, and whether you can have something like a network of brain regions in a network of people also, and how this will change this. I think this is a really interesting question, and it's something that I put myself in the cognitive neuroscientist category. We tend to ignore, exactly like cortical central analysis tends to ignore the basal ganglia.
I know of some groups that are doing studies, EEG studies with like a teacher in a classroom. You have a instructor and they're, monitoring the students' brains and looking at synchrony between the teacher and students and things like that. And there's other work using hyperscanning, where you have two individuals in two different MRIs interacting with each other. In fact, you can even do between brain Granger causal analysis to see if what's happening in one brain causally affects what's happening in other brains. So there's quite a lot of work looking at social networks and brain networks in this way. I don't know if that's what one of the attendees was asking about. Well, yeah, movie watching. There's quite a lot of naturalistic stimuli that's become quite popular now. So yeah, definitely a lot of work out there.
I totally second that. I think in general, people in our field, human brain imaging, are more and more critical really of the paradigms we've been using so far, which are very ecologically non-valid or contrived. Putting a person in a scanner and instructing them not to move, and then have us behavior, maybe a button press, but that's it. It's not really an ecologically valid attempt at looking at how brain and behavior interact with each other, really. But of course, methodology is difficult, right? So that's actually where EEG comes back in. I think being portable and being somewhat robust, with respect to noise and so forth, it's actually a great technology to bring back into the real world and allow recording from multiple individuals. So resting state, actually, in my view, I know it's been much maligned, especially by people who are more cognitively inclined, because there is no task instruction and it's unconstrained and task-free. I actually think resting state is more ecologically valid somehow than some of those very artificial seeming task manipulations that people have to undergo in scanners. Because after all, when you think about what you're actually doing most of the time, what your brain is doing most of the time. A lot of that spontaneous, seemingly undirected cognition is going on. And so in some strange way, it has gotten us away from these very constrained task settings into a more ecological mode. And now perhaps it's time to leave resting state behind and actually go more to more engaging, socially and cognitively demanding environments, and once again ask the same questions, but now in a richer setting.
Randy, do you want to add anything?
I can just add that, I think looking at maybe complex decision making is another domain that might be interesting. A lot of what people do could be construed as decision making. In my group, we're actually looking at social decision making, which gets at the social aspect and involves kind of collaborative elements as well as kind of individual cognition. And so, that may be a good framework for, integrating things like the insula and value and motivation and all these different elements that really come together in the brain areas. So I find that to be one of the more kind of ecological ways of thinking about a kind of cognitive task, as opposed to like, the Stroop task or something, which seems very artificial in most situations, yet is, what we tend to study, or the NBAC. Oh my gosh, that's just not what we do. So yeah, I think paying attention to kind of like which tasks are really at the centroid of kind of everyday cognition would be really interesting.
Yeah, there's a lot of work that in cognitive ontologies now that's really trying to say, how many actual processes are there? And we have some work, I'll just throw this out there, that we suggest there's really only 4, and you really only get like 4 activation patterns across, hundreds and hundreds of tasks. And we've been calling them by many different names, but it can be distilled down a little bit more. Once you get into these meta-analytic approaches, you see more of the commonalities rather than the differences.
Wait, what are those 4?
I'll put the link in the chat.
Is this something you believe in, or what's your thought about
so
that?
It's a data-driven approach where we took, all the maps that are available, all the unthresholded activation maps, and basically clustered them and came up with these, 4 recurring patterns. I'll put it, yeah, I'd have to show all the slides to really explain it. But the idea being that if you use sort of data-driven ways, instead of saying like, we know that there's working memory, if you just say, what are all the tasks out there? And then try to subdivide them by their actual activation patterns, unthresholded, without any assumptions, you do get very few, like these are some neuroinformatics papers that my group and others have put out, but you do just get very few patterns that explain a whole range of tasks. And I think there's oftentimes, because we come from cognitive psychology or cognitive science and then move into cognitive neuroscience, we bring those cognitive architectures with us, whether or not they have a biological differentiation. We just assume that they're going to be separate. Oftentimes they're not.
So if you try to put like a label on the 4 things, though, just for exposition here, is it possible to label the 4 things? I'm just really curious. I haven't heard of this before. And you're muted, Lucina.
Oh, sorry. Yeah, I was just trying to see if I could. Can you hear me? Oh, I was seeing if I could find. Yeah, this was a student in my lab who left the lab a few years ago, so I can't even remember what the 4 things were. So I'm putting it in the chat here.
Thank you. We're running down to the last few minutes of this panel discussion, and too bad that Matt Botvinnik is not here because he had to leave early. But I would like to bring it back to actually where this session started, which was these models of deep learning. And of course, there is a lot of speculation that has already been asked about, how similar the brain is to a microprocessor or to a neural network model. But what do you think your work says about the progresses that's been done in neuroscience and the progresses and the new models that are showing up in deep learning right now? I'm going to call the speakers by name, and I'm going to start with Randy.
Sure. Yeah. So, I think as we were kind of discussing a little bit with Matt there, I think that the deep network models are really leveraging a lot of the elements that we think are important, from a cognitive perspective and a cognitive neuroscience perspective, like the ability to do this kind of pattern completion, cued retrieval of memory. So all the kind of core elements that we think of in episodic memory retrieval and just general kind of semantic knowledge, the ability to kind of put together subsets of information and kind of bind them and retrieve them, that's a core element of these new architectures. Also, attention, right? Matt talked about attention as a critical element of the transformer architecture. And that's obviously something that, cognitive people have been talking about for a long time, how attention can be used to bind and to select. And so those kinds of basic cognitive operations, I think, are being captured in the deep networks. And it is kind of like what Olaf mentioned, like this idea that, it's like an alien intelligence, right? It's doing this in a way that doesn't obey the same kinds of constraints that we see in the brain, right? And so they can create these really tightly connected kind of parcellated architectures that replicate like, an entire cognitive architecture n times in parallel and then n times deep, stacked. And so you're taking things that are operating over time and over, I don't know, across different areas and just kind of doing them all in parallel. And it's just kind of like mind-boggling, how much stuff is happening kind of in parallel in these models that I think really is something that operates over time in a sort of much more integrated cognitive system in people. And so, I think that, there's been a few brief mentions of consciousness in the discussion, and this notion of like this kind of global workspace, kind of coherent, integrated sense of like unitary aspect of consciousness is part of the fact that is a reflection of the fact that our brains are really kind of these interacting systems that are very much more coordinated and globally interacting rather than these deep neural network architectures that have really kind of parallelized all this stuff. So I think it's, it is kind of like seeing like an alien octopus kind of brain or something that's being developed there. That's my sense of it.
Randy, can you write that in a paper and do it, publish it at Science or Nature or something? So I can
I'll try it. Yeah.
That is, I don't know, maybe everybody else doesn't agree with you, but to me, that was a really good summary that I would love to be able to point to.
Cool. Yeah.
And I think one reason why there is this, I agree with Randy entirely. I think one of the reasons why there is this sort of divergence to some extent is that biological brains always have a body, and behavior has to actually unfold on a certain time scale in the environment, and is subject once again to severe penalty if it's maladaptive. So there's this, an AI system doesn't have that unified need to produce a single output, right? Or do one thing. We act in a unified way. I think that's why we're seeing the high premium put in brain architectures on integration. That's perhaps a little bit less critical for some of these deep nets that really don't have that pressure on them. And so they can go off, they can evolve, they can adapt in a very different direction. And again, not to abuse the analogy, but it is a little bit like an airplane versus a bird, right? I mean, no one wants a bird if they want to go, on vacation to Europe. You don't get on the back of a bird and ask the bird to fly you there. That's not going to happen. But birds can do things that airplanes can't do. They can perform remarkable feats of takeoff and landing, and they do other things too. They have offspring, they sing, and things like that. I mean, it's totally different. It's a totally different part of the space that we're in, right? And yet there's the same sort of underlying physics about the air and aerodynamics and whatnot. To compare the two is really kind of limited, right? And I feel like AI and deep learning is more where the airplanes are. We want airplanes. We want them to help us in our pursuits. but it is not the same thing as a biological system.
Lucina, do you want to add something?
Yeah, I completely agree. I think this whole field of embodied cognition really thinks about the brain in space and the brain in the environment. And, you know, exactly, it's not the same as brain in a vat or you know, AI in a vat. So I think that's really always important to keep in mind. I spend a lot of time with consciousness people because I'm part of this brain, mind, and consciousness group in the Canadian Institute for Advanced Research. And I just, if it makes anyone feel better, we've been meeting for years, you know, several times a year, and you know, people with Dan Dennett are in the group. We have never come to any consensus. So if it makes anyone feel better, the consciousness group hasn't decided on what is consciousness.
So I think we have reached the allotted time. John, I don't know if you want to stop the recording and continue the discussion, or what is the best way to move forward now?
So I just want to start by thanking you for running this. I thought this was a great session. I also am going to encourage the four of you plus whatever. So I hope that someday people point back and say, oh, the reason we started the symposium on neurocognitive architectures was because of VISCA 2021. But I think that this is a field that bringing together the cognitive and the neuro and all that. I mean, this is something all of you have been doing, but I'm just hoping that this brings some more people into that. And I really thank all of you for exposing the broader audience to these ideas. So thanks a lot. And I'm going to stop the recording now. I want to